All right, thank you for being here. Happy Thursday. So today, I know at least some of you have turned in lesson one already. That's great. We'll take a few minutes just to work through the mutual friends. And I'm gonna try maybe so like we don't have to all figure this out individually. Um, maybe meet with like a pair of your closest neighbor, or for you guys, maybe a group of three, unless someone else shows up. Um, and so just take a minute or so to try and work through this mutual friends problem. And then once you're done, turn in the notebook to Canvas. And so just a reminder of where we're at. I did update the README with the Windows link. So just so you know that. Hello. Um, let's see, where are we? Over here. We were at exercise 3, which is if we've got a graph, let's print that graph again. No, run all of them. Okay, so if we've got this graph of friends, and we assume that we're given two nodes, so two people, and we want to find what mutual friends do they have, right? So Alice and Esther should have Claire in common as a mutual friend. So how do we get that? Okay, so find a partner nearby. If you've done it, then great, you can help your partner try and don't just like give them the answer, but help them like think through it. And we'll take a few minutes and work on that. Yeah. All right. Someone tell me what to type. How should I solve this problem? Go for it. Let's do it efficiently.
Then I had neighbors one. This.
Did you know you can duplicate lines by, for me, it's Option Shift down, or for Windows, it's probably Alt Shift down.
But, and then after that, I just used a for loop. So I did four neighbors, neighbors one, neighbors is equal to seven.
Uh, let's result append neighbor, and then just scroll down. Return result. Go. Wait, what should be parentheses?
So
Regular parentheses, not square brackets. Check mark, check mark. Great. Okay, so I know other people did another version, so let's maybe if I spell it correctly. Node 2. Someone want to give me another version? I mean, like this absolutely does the job. Great work. I just want to, I know there's other ways of going about it too. Yeah,
Copy the neighbors one, neighbors two line for it. That's how that's to do that.
okay. Sorry.
Very, very good. One of the one side.
What? Explain to me what this is doing.
Setting. Turn.
Okay, cool, cool. I haven't seen this used as an intersection before. Absolutely gonna start using this. Anyone else have like a variation of that? I know I saw some people using set and or wait, no, this does use set. Um, any other ways to do this return? Yeah. Okay, so I think that's neighbors one here. Wait. Oh, like also the intersection? Okay, so the difference here is you just make it sorted. Okay, cool. Awesome. Thank you. Great job. Okay, so this is just the aside about directed graphs, where initially, let's go back up here where we very first defined a graph. Where is it? You're up here. Which is just nx dot graph. This is an undirected graph. If we wanted to have a directed graph, then we have to specify that. So scrolling all the way back down, which is we have to say it's a digraph. And here, when we add things to the digraph, then the edges matter. So let's execute this one. Here we have an edge from 1 to 2, and so we see that with the arrow. An edge from, let's say, 3 to 4. So now the direction matters for the edges that we have. And so with that, because it's directed, bless you, if we check if there's an edge between 1 to 2, yeah. If there's an edge between 2 to 1, no, because it's not true for digraphs. And so the notion where we were talking about like the in degree or the out degree of nodes that are in a directed graph, the successors, those are the out degree. And this is, or not degree because it's a list of nodes. And these are the in nodes. And so this the predecessors are like what points to this current node, which is 2. The successors are what does 2 point to. And then we can get those numbers with in degree and out degree. And so that gives us the in degree, which is the number of predecessors, is 3. The out degree, which is the number of successors, is 1. And then they've got the caveat where, oh, wait, no, I don't want to ask Copilot. So you got to be careful if you're trying to use degree because it'll give you the out degree plus the in degree, which is 4, which is not correct. Like, I mean, it is correct in a way, but like it doesn't give you necessarily the information that you want. So just be careful about that. And successors work, but neighbors, because we're in a directed graph, we need something more specific than just neighbors. Or wait, no. Neighbors gives us wait, what? Are we still looking at 2? Wait, the successors of 2. Wait, this doesn't make sense. Oh, wait, no. It doesn't make sense. We just swapped the order. So the successors of 2 is the node 3. So there's one successor. And when we call neighbors, it also just gives us the successors. So just keep that in mind as we go forward. All right. So if you wouldn't mind taking a second, if you haven't already, submit this one to Canvas, to the lesson 1 assignment. And then we'll go ahead with lesson 2. Go all the way up to the top. Right. Very good. Cool. All right, so open lesson 2. So for this one, I also have to select the virtual environment just when I run the import statement. But if I do that, then we should be good. Okay, so this one talks about paths, connected components, all that good stuff. So here we start with a graph, and then we add nodes 1, 2, 3, 4. Then we say here are the edges. And then we can draw them like that. Note that when I run this multiple times, the graph may move and change around. That's fine. But we've got this sort of triangle with an appendage. So we can ask if there's a path between 2 vertices. So is there a path that connects 3 and 4? 3 is over here, 4 is over there. The answer is yes, we can go through 1. We can also ask to list all of them. So in particular, all simple paths where there's, yeah. So something without any cycles. So the way to get from 3 to 4, the obvious one is go through 1. The other one is to go around to 2. So 3, and we go around to 2 and go the other way. 3, 2, 1, 4. Okay. And so once we have these, then to find the shortest path, we just ask, what's the shortest path? And since this one is length 3 as opposed to this one of length 4, then this one wins out. Or if you only want to know what's the length of that, there's a function for that too. This is so something to keep in mind as we go into the assignment and then later the project, which I'll talk about in a bit, is if you get to a point where you're like, I want to know this information, there's probably a way for this to happen. I encourage you to look at the documentation, read through it, and see what sort of functions are available, because they've got a lot of them. And so chances are it's there somewhere. So this is a note. No, don't copy it. The path length is defined by the number of edges. So which may be different than what we assume. Where the distance from 3 to 4, we only go to one node, but there's 2 edges there. So keep that in mind if you are wanting to instead measure the number of nodes that you pass through. In terms of connectivity, we can do a similar thing to ask, is it connected? And remember, this is for undirected graphs. And so here we've got a graph where we've added a cycle of just 3 nodes, so K3. And then we add an edge from 4 to 5, which are 2 nodes that don't yet exist in our graph. And so we've got 1, 2, 3 over here and 4 and 5 over here, all over by their lonesome. And so then when we ask, is it connected? We get no, because there are 2 disconnected structures. There's no path from 4 or 5 to 1, 2, or 3. And we can ask that when we say, does it have a path between 3 and 5? And the answer is no. And moreover, if we try to say, give me the shortest path between 3 and 5, it gives us an error because there's no such path. And so it gives us all of this error messages, and then finally it says no path. We could find the connected components as well, where since we've got a cycle and then K2, then there's 2 connected components. Let's try, maybe if I say g dot add edge of 6 and 7, that should give me 3, right? So if I do that, and then I go down here and say number of connected components, now I get 3. So number of connected components gives us how many. If we just ask for connected components, and we put them in a list, then it gives them to us. It's in set format, I guess. So let's see what happens if we just, okay, yeah. So they're in set format, but they're generators. And so in order to see them, we do need to say, make it a list so I can look at it. But again, like before, we can always, if we don't want to put it into a list, we can always iterate through it and get it that way as well. We want to find just the biggest component. We can do that. So we ask, give me the max of this, and we give it, here's my generator object of connected components. And to say, we have to also specify, what are we saying? What does max mean? Like, do we mean what's the biggest number in any of these or something like that? No, for this we need the length. So we're only judging by the length. That's what we mean by max. So doing that gives us 1, 2, and 3. So if we only wanted to see that component specifically, they call this core nodes, and then we still have that. So this gives us 1, 2, and 3. And then what we can do is we can make a subgraph of that. So make it its own graph by saying, here's the nodes. So give me a subgraph of this graph G, and then just draw that. And that gives us 1, 2, and 3. Okay, so for the digraphs, this is a little bit different. So on my computer, we've got all of these edges, and then we draw it. This is just our directed graph. And so for paths, it works similarly, just with arrows on the edges. So is there a path between 1 and 4? We have to go from 1 to 2, 2 to 3, and then we can go to 4. But we can also go around and go through 5 and 6. So 2 to 5, 5 to 2. So when you swap the vertices, you're going to get maybe different paths because that's how directed edges work. And then remember, for digraphs, we have a different notion of connected components, where there's connected, which is if the connected but not connected is when the underlying graph, so if you take out all the edges, or if you take out all the arrows, if that underlying graph is connected, then the digraph is connected. But strongly is when if there's a path from any one vertex to any other vertex. And remember, that's like the city full of one-way streets. Can we get from one place to another place in our city without, or by taking a sequence of streets? And so networks has a way for us to see, is it strongly connected, weakly connected? That's just the underlying connection part. But the default is connected, which works for undirected graphs, does not work for digraphs. And then similarly, we can get, here's the components for weakly and strongly connected. And then we're off to the races for activity. Okay, so I need to fix this. So I need to fix the path for that. So there's a graph in the data set that they provide, which says, here's all the flights from one airport to another. So see, ANC is Anchorage, IAD is Washington Dulles. I wish I knew what these airports were. Does anybody know off the top of their heads? I'm guessing this may be like Philadelphia or something, but I don't know. Anyway, these edges are directed, right? Because there may be a flight from, I don't know, Oakland to San Francisco, but there may not be a flight from San Francisco back to Oakland, right? Where maybe Oakland feeds into the larger hub airport, but not always does it go back the other way. So that's the idea of this graph. And we've got nodes, but those nodes also have some sort of attributes to them. So we've got this IATA code with the 3 letters, and we've got the full name, and also some information of where it's located. So let's open. This is a graph ML. So, okay, so I can't open those because I think they're compressed. But this is a graph ML sort of structure. So is anyone familiar with XML? Okay, it's a kind of way to describe some information. So these files are kind of everywhere. So part of them are like VS Code uses them to say, here's how to execute this environment. It stores some sort of data. And so here it's got, remember like dictionaries where we have like key and value? You can structure it kind of like that. Okay, I'm actually really curious. So I'm going to take a second and figure out how we can um, open that. Does anybody remember how to unzip the GZ files? Let's try, what's the flight name or the data name? Open Flights USA. No. Let's try another way. That work? It did. Okay, so let me tell you what I did. First I went there so I went into the folder and then G unzip and then the name of the file unzipped it for me. This may not work on Windows, but I think it may be worth a try if you want to see what it looks like. So and you can see like the reason that they zipped this file is because it's 6,000 lines long, which kind of makes sense. But let's kind of look at what this is. So we've got, let's see if we can find Oakland. There we go. So it's a series of nodes, right? So we've got the node ID. That's how we refer to it in our program. And then there's three things like D0, D1, D3. 0, that's the full name of the airport. I'm guessing this is latitude and the other is longitude. And then we've got here's the IATA code. So all this data is stored in the XML file. And so up here it says, here's what D0 means, here's what D1 means, here's what D2 means. Does it say what D3 means? Oh yeah, it does. And D3 is the IATA code. So we can look at this XML file and kind of piece it together. So we've got a sequence of nodes, which makes sense. Like here's each node in our graph. And then we've got a series of edges where we've got the source and the target, which is where do we start? Where do we go to? So this is the directed. So there's an edge from RDM to Portland. Okay, so that's kind of just what that file is. And so because of that, because we've stored it in this format, then we can have, when we look at like, what's this node, it can tell us information. And so this is one of the things where graph theory is like really, really useful, because not only do we have this relationship that's represented, we also can have additional data that's tied to each node. So like we can say, here's Indianapolis, and it's got a latitude and longitude, here's where it is, which are things that we might want to know about an airport. And so if we have the attributes stored in this way, we can access it like it's a dictionary, where we can say, I want to know the name or the latitude, where we can get these different aspects about the airport. Okay, so now we've got a series of 3 exercises, which I would like you to work in your groups again, where first find, is there a direct flight between Indianapolis, so Indianapolis is IND, and then Fairbanks is FAI. Also, let's see if there's a flight between Oakland and San Francisco, and vice versa. And then choose your favorite 2 airports and see if there's a flight between them. So that's the first exercise. The other one is, so if there isn't a direct path, we want to find what's the shortest possible path. So I'm guessing if this is exercise 2, then I'm guessing that the answer here is no. But if you want to fly from one to the other, what's the shortest path? What's the fewest number of flights you have to take? Fewest number of connections. And then, can we travel from any one airport to any other airport? This seems like a fairly easy in my mind. I know there's like a function that's going to give this to me. So work with your partner, figure these out, go for it. And we'll try and find this. Okay, so how do we find if there's a direct flight between Indianapolis and Fairbanks? Tell me what code to write. Someone who hasn't gone yet today. There's only so many of you. Go for it. All right. And that's false. Let's see. Heads edge from SFO to Oakland. Also false. Let's see. Do they have Lincoln? They do. So one of the things when I was living in Lincoln, it pretty much only goes to like 3 places. One of which is Denver. So absolutely there's an edge between those 2. Okay. So how do you find the shortest itinerary? If there's no direct edge from Indianapolis to Fairbanks, how do you get there? Someone else. Would you like to go? Man, this is really annoying. FAI, right? Yeah. So this looks, is this Boston and then Seattle and then Fairbanks? Okay, sounds good. Let's try, for some reason, if we don't want to drive 30 minutes, we have to go to EUG. What's EUG? Maybe that's Eugene, Oregon? Okay. Um, all right. Um, and then I don't know, someone give me another of their favorite airports. I don't know. Let's see if we wanted to go from Oakland to Lincoln, which I know you would have to go through Denver or MSP. MSP. Minneapolis? Okay. The point being that like you have to take a connection. Okay, so then how do I answer this question? It should be just one line of code. Someone please volunteer. Go for it. E and then, or no, just G in general. False. Let's see, what are do I want to know what all of them are? Maybe not. If there's like a million of them. Yeah, no, I don't think I want to know what that. Um, wait. We had code for this. Strongly connected. Da, da, da. Okay, so first let's go down here and see how many connected components there are. There's 3. With labels equals true. No, forget what the command is. Oh, that should be it. We need SciPy for this? That's annoying. Um, sorry. What's the command? Python 3-m pip install SciPy. Okay. I want to see what this graph looks like. Okay, so we've got a whole bunch of things over here. And then we've got like, it looks like maybe three down here. Where's the third one? Yeah, I don't know. Um, what if we say without? Okay, maybe that's okay. So I just want to explore. Like I want to know what are the connected components. Um, so I don't know. First we'll make a subgraph of that, and then let's say or dot number of nodes. No, that's not going to give us it. Um, okay, so the main part has 539 airports. Let's try min, which I think should have, so I think maybe we have only three. How do we find, okay, so I didn't plan this ahead. How do we find the number of, so if we've got like 539 and three, whatever, I don't know for sure. Like I can look at this and maybe guess that like this maybe has more than three, judging by the shape of the blob. But how do I know? I would like a list with like 539, some number, and three. How do I find that list of like the length of the connected components? How would I find that? So we can get, here's my thought. So we can get the connected components. Um, and then if we find the length of that, that gives us three, right? Because there's three connected components. But maybe we iterate through that. So it's probably a faster way to do this. So if I want the list with the lengths, then for components in the connected components, comp lengths dot append the length of that component. Nah, no, go back. That makes sense? I think that might give me what I want. Because the connected component object should be iterable. No. Okay, maybe we don't do that. Oh my gosh, it did it. Okay, so we've got one big node and then the other one. How would I print? How would I like? There's 3 and 4 airports in those, so I would like to know what they are. How do I get that? Right? I feel like this is part of what I like a thought process that I want you to be thinking about as you go about the homework and the project later of like we can do these really simple things, but when we're talking about like airports, the application, I think it makes sense to ask, oh, what's this disconnected set of airports or this disconnected set of airports? And like, which airports are they? I think it's useful information to know. The only question is, how do we write code to get there? Any ideas? So we know we can get like, we can iterate through the components and we know how big they are. So maybe we say if, or, okay, so let's say if I know how big they are and it's only two cases, um, size is equal to the length of that component. And so maybe if size is less than 500, print this component has, and then maybe e dot nodes and maybe give it the component. No. Okay, so this is where if I get stuck on this and if you are stuck on this in the homework, this is where I turn to Google. And so maybe I go networks, find nodes in components. Okay. So first is Stack Overflow. Next is the actual documentation. So maybe let's look at that one. Returns the set of nodes in the component of graph containing node n. Okay, so maybe we need like a specific node. We don't know that. So maybe that's not what we want. If we just look at like the regular components, that doesn't give us. Okay, so let's look at the Stack Overflow. So they've also got a series of, they've got a disconnected graph, but they want to know which nodes are here. Oh, no, it gives us the same answer. Node connected component. But there's got to be a way to find. Oh, maybe if we could make it a subgraph. Um, equals g dot subgraph. I don't know if that's that's not gonna work. Or maybe it does. Okay, so then sg.nodes. Oh, that worked. Okay, so we made a subgraph of the components. So we can iterate through all the components and then make each one a subgraph. And then we can just say, give me the nodes of that subgraph. And that gives me these guys and these guys, none of whose airport codes I know off the top of my head. Let's just see, what's airport? Alaska. I'm guessing maybe this is, let's see, BFI Airport. Springfield in Washington. Okay, so maybe these are like the, I don't know, because there's like, what am I trying to say? I think like the node maybe around Alaska makes sense because you would have to, but then that would mean, according to here, that you can't get from any of those like regional airports out to the main network. So maybe you have to take a boat or something. I don't know. Okay, but I'm glad we solved it. Hooray. So if you're trying to figure out something like this, don't give up. Try different things. Use Google. Google is your friend. And so, yeah, and then get to a point where like, now I have this manageable series of data. And so I just look like, what are these airports? Where are they? And what does that tell me about the region? Why is this graph disconnected? Those are the questions that I'd kind of like you to answer. Okay, so I want to talk about the homework assignment. So on Tuesday, we'll do lesson 3 and then maybe time to work on the homework in class. But the idea is you make a Jupyter notebook, or if you just want to do a Python file, that's also fine. And find some data. So either you can use some data that's like in this datasets file, you can choose one of them, or go on the internet and find some other piece of data. This is like very, very, very small restriction, but I want to have you start thinking about bigger applications. So go on the internet and search graph data set, and then figure out how to import it into the networks variable. Be able to draw the graph so it looks pretty. So play around with like the NX dot, where is it? I don't know, like the NX dot draw settings, play around with that so it looks good. And then choose several functions, maybe connected components or some things. We'll talk a little bit about centrality on Tuesday. But like choose some functions and say some things about your graph. And so for that, I would expect you to just add like down here, you can add like a markdown cell, or in Colab, it might show up as text. And so you can say things about your graph. And I would like to know your thoughts. And so then that's just submit the notebook and your data. And so all that should be there. I will note that this saying something about your graph, that's going to be good practice for the project. So I'll have a full write-up, but I'll just let you know now that like the project is basically this, but bigger. So there's a larger requirement for the size of your graph. And you do this whole process, and then eventually you'll write maybe like a 1 to 2 page summary of, here's the data that I chose, here's why it's important, here's the functions that I used, here's what it means, And here's what we can say about this graph in like its real world applications. So that's kind of the preview of the project. Okay, let's see. The project, I think, will probably have groups. We've got 1 minute. Do you want to do the homework in groups? You can if you want. If you decide on a group being pairs, then come let me know, and I'm open to that. But the only requirement is that your graph has to be more complex and say more things about it. Okay, that's all I have for you. If you want to do that in groups, come talk with me. Otherwise, go ahead and get started on it, and I'll see you on Tuesday. Thanks for being here.